In this illustration, we'll discuss about a block sliding over another L-shaped block. Here you can see the figure shows a block of mass small m is sliding on horizontal part of a L-shaped block of mass capital M, which is at rest. Here all surfaces are smooth and it is observed that a small block leaves from point A on vertical part of M in upward direction as seen from M. And here we are required to find the maximum height attained by this mass m above ground and a speed of m at point A. So here we can write when the small m starts ascending up the vertical path due to normal reaction, this capital M also starts moving in horizontal direction and this will be raising up on this block. So here we can redraw the picture and we can see when the small m mass reaches point A, say this small m reaches this point, it will be having a horizontal velocity v1 and upward velocity v2. So when it will be leaving the block of mass capital M, here we can see in vertical direction its speed as observed with respect to capital M will be only v2, and as we see from ground it will be moving with the velocity of capital M also, or both would be moving horizontally at a velocity v1. So we can write when small m reaches point A, if both blocks are moving at velocity v1 horizontally, here we use by linear momentum conservation mu should be equals to m plus capital M v1, because the total horizontal momentum of system must remain conserved, which gives us the velocity v1 of a block as well as L-shaped block in horizontal direction, which is mu by m plus capital M. Now, as it is at a height h above the ground, here we can write by work energy theorem, we have initial kinetic energy of the system was only half mu square, and when it reaches a height h, and we can neglect the initial height of this horizontal section of L-shaped block, so it is minus mgh work done against gravity is equals to the final kinetic energy. So for bigger block it is half capital M v1 square, plus for a smaller block it is half m this v1 square plus v2 square, as it is having the two velocity components. So to find the maximum height above the ground level, we need to calculate the value of v2, for which here we can substitute the value of v1. So this will be mu square minus 2mgh is equals to, we can see this half m plus small m can be taken out, and v square we can write as m square u square by m plus capital M whole square, plus this will be half m v2 square, and in this situation this half gets cancelled out because I have already taken 2 LCM on the other side. So here you can also write it as half and cancel this 2. And further simplifying this expression, we get the value of v2, which is equals to, in this situation we are getting u square multiplied by 1 minus m by m plus capital M minus 2gh. You can simplify this and verify this value, which can further be written as capital M u square by m plus capital M minus 2gh. Now we can continue here to calculate first the velocity of small m at point A, which is root of v1 square plus v2 square. We substitute the values of v1 and v2 from here. You can see this velocity of mass at point A we are getting is root of just substitute these two values and simplify. The result will be m square plus capital M square plus mm divided by m plus m whole square minus 2gh, which is one result of this problem. And if we wish to calculate the maximum height attained by small m above ground level is, this maximum height can be given by small h plus v2 square by 2g, because vertical motion is a free fall motion with the initial speed v2 when it breaks off from this bigger block. So on substituting the value of v2 over here, we are getting the result as u square by 2g multiplied by m by small m plus capital M. This is another result of this problem.